problem is given that a cast iron element is subjected to the following stresses as presented in figure 5. So this is figure 5 here, this one here. And we are asked to determine the component, if the component will fail, using the two failure theories for brittle materials seen in class, the lectures. And we need to consider that the ultimate strength in tension is 280 megapascals, and the ultimate strength in compression is 410 megapascals. These are the state of stress cases we're given, so we have 3 cases. So let's imagine that that's kind of a point, or 3 different points in one piece or in one machine element, and we need to determine if, according to these 2 theories and according to this state of stresses, these elements will fail. Yeah. Here I have drawn a quick sketch of Rankine's theory, or the principal stress, maximum principal stress theory, and Mohr's theory, also known as Coulomb's Mohr theory. Yeah? So this red one is Coulomb's theory, and look at it forms some sort of rhomboid here that goes to the ultimate strength in tension, ultimate strength in compression, and forms this shape. Now Rankine is just some sort of kind of square shape area. Yeah. So intuitively we might see that one piece or one stress case might fall either here or here. So it means that for one theory, the material won't fail according to that theory, and for the other, it definitely be safe. So we have 3 cases. We have the stress elements for all those 3 cases. What we need to do then is to build the stress tensors and then find out how much are the principal stresses, and then use the theories to determine if they will fail or not. And before doing that, it would be nice to have already these values here, so we have it as reference. So this is the ultimate strength in tension, and this is 280. Now I want to draw it or write it with this color here. This is 280 megapascals, same as in here. So 280 megapascals. Then we have, for the compressive state, ultimate strength is, I'm going to put it negative because we are in here, and we're going to be using the notion of quadrants to determine which part of the Mohr's, for example, law, the failure theory, applies to which. So this is going to be 410 megapascals, and this also is going to be 410 megapascals. Here, minus 410 megapascals, like this. And let's draw here something like saying we have 3 cases. We have case 1, then we have, put it in the middle, case 2. Awesome. And then we have case 3. Trying to organize space here. So first, let's convert this into our stress tensor shape, yeah, just for practice. So we're going to have here the stress tensor. I'm going to do 1. Yeah, it's going to be, I'm going to do it kind of straight here. I'm going to omit the units because everything is going to be megapascals, and any calculation we do from now on, most of them, I believe all of them are going to be megapascals, so we don't need to be mixing units here. So for the case 1, which is this one, I will put it like that. This is case 2, and this is case 3. We're going to have normal stress is going to be positive according to von Karman convention. This is going to be 200. Shear stress is going to be positive, again, according to von Karman convention. Look at this. You cannot see, well, in the exercise sheet is better, but here we have this normal stress is pointing upward, which means is in the negative phase, which indicates that this one is negative, like this. Can we do simultaneously for cases? Yeah, it's better. So because we're on the same path. So for this one here, we're going to have what? Then this normal stress is negative, this normal stress is negative, and then the shear stress is positive. All right, so let's do it. Minus 200, 100, and then here we're going to have 100, and then minus 120. Then for the third case, we're going to have, this is positive, positive, positive. All of them are positive. So 200. I had an error here. It's kind of just confusing things. Just need to double check this. So this is 50 and 50. Sorry about this. And then let's continue with case 3, and this is going to be 100, then 100, again 200. Just need to double check that I have everything in place and put it a little bit up here. Perfect. So let's see, 200, 100, 120, 200, 100, 120. Orientation is correct. Then I have here 250, 120. Yes, and then I have here 200, 100, 200. Perfect, perfect, and perfect. So let's start with the first case. Let's find out the principal stresses. And now this is a plane stress case. Yeah? And if it's a plane stress case, we could use a simplification to the characteristic equation of the stress tensor. And this basically says using sigma 1 and sigma 3 as extremes in the values of the principal stresses. Now this is going to be equal to sigma 1 plus sigma 3. This is the average of normal stresses plus then square root of then this value here. Oh, trying to delete this. 3. Oh, sorry about this. This is not the way to do it. And I'm going to show you why, because this is a redundancy that is not coming there. I just, let's see if I can delete this one to make it a little bit bigger before correcting this atrocious mistake. So this doesn't make sense at all. Yeah. So this is x, y, then plus the shear stress xy square. Then I can close my square root. As this is getting in the middle of things, I'm going to just move all of these and put it here. Yeah, I'm going to give it a title. Principal stresses formula. Principal stresses formula. Then here planar case. Like this. So let's apply then to, I'm going to apply to the first one, yeah? And then the other two cases, we are going to just input values in the formula directly in the calculator. So let's take it, because it's going to take a lot of space here. So it's here. So I will write it first, and then maybe I will delete it, but I just want to show how it goes. It's going to be 200 plus minus this divided by 2. And again, I'm going to bump into this other case. Let me put it down here, yeah? Plus square root of 200 minus 120 divided by 2. And this is going to be squared. I don't like it. Like this. Square plus this one here. But let me substitute it. This is, we're talking the first case. The first case is 100 here. How much is this one? Let's go to the calculator and say, all right, again, I don't know, I'm missing things here. There's plus minus. Okay, this is plus minus will give you the two extremes of the principal stresses. Apologies for that. Then let's go here. So the first one, it's going to be 200. Actually, I should start like this. Minus 120 divided by 2 plus square root of, let's open this parenthesis here. Yeah, parenthesis here, and 200 plus 120 divided by 2, and this is square plus 100 square. And that's giving me 200, nope, this one, 228.679, let's call it, megapascals. Which means that this one here is going to be the same. Well, we could use the previous, but take some minus here. And that is 100 minus 148.679 again, megapascals. Now we have this one. Good thing about this software is I can write this one like this. It should give me a perfect rectangle. Awesome. So this is the way we calculated it. We're going to do the same approach for cases 2 and 3, and then we start designing how things work, okay? But I want to get rid of this because we're not going to use it anymore. Here, I can delete it. And I can take these spaces here and delete this also. Then I can take these ones and move it up. Okay, let's jump then to case number 2. I should have a formula here. That would allow me just to substitute values, but can I do it? Let's see. Equation 1 in terms of x, y, z. Should have done this before. So if I call x equal to sigma x, y to sigma y, and z to the shear stress, so this is going to be equals to this divided by 2 plus, is there a plus minus here? I wonder if GeoGebra has a plus minus. Parentheses, and then x minus y divided by 2. This is square plus z square. I hope it worked. I got it. So let's take, for case 2, I'm going to have that's going to be equal to equation 1 evaluated in minus 200, then minus 120, then 50. Yeah, so is it giving me this or not? Ah, but my bad. Equation 1, sorry about this. Again, minus 200, comma, minus 120, comma, 50. There we go. So we have in our case here that this is going to be equal to minus, this is sigma 1, yeah, minus 91.968 megapascals. So megapascals here. Yeah. And then sigma 3, basically I could duplicate this input. I could call it equation 2, that is in terms, or no, it's not going to allow me. But nothing can be perfect. So let's see, x, y, z, good exercise to write this all, and this is going to be equal to, again, x plus y by 2 minus, this time, square root of parentheses x minus y divided by 2. You get to know these equations by heart, plus z squared. Perfect. Then for our second case, I have equation 2 evaluated in, again, minus 200, minus 120, 50. There we go. So we have, how can I, yeah, it worked. So minus 224.03 megapascals. And we have the second, like this. Beautiful. And so let's go for the third case. In the third case, we have, again, I need to use equation 1 for sigma 1, and I need to input 200, 200, 100, 300 megapascals. Look how fast this goes. All right, here, black, so sigma 1 equals to 300 megapascals. And for sigma 3, I need to use equation 2, evaluated again in this 200, 200, and 100. Give me 100. Here, 100 megapascals. Like this. Perfect. Now, just to be a little bit symmetric with things, I can just move this a little bit up. There you go. Now, you have a couple of options to answer this question. If you had a drawing like this made a scale, so you could just plot these values here and see how things go. For example, let's take the first one. The first one says that, sigma 1 is 220. So you would go here 220, maybe here, and then you would go down 140. So maybe here, I don't know. So it would be something like this. Let me see. It would be something like this. Yeah, but you have to have it. You have to have it, to the millimeter, so you can plot exactly how things go. And then by just inspecting if the point is within or outside of the area, then you can say that according to Rankine or according to Mohr theories, they fail or not. Yeah, but we don't have that in this case, so we need to do it kind of analytically. So let's take the first case. So the first case is a point that, and I'm going to write it here, is located. And this is where the location is important. Located in the fourth quadrant, like this, fourth quadrant. Meaning that that point is going to be located in here. In this quadrant, Rankine and Mohs theory, they differ largely. I would say largely, yeah, because if you're here, you are good with Mohr, but you're good with Rankine. But if you're here, you are not good with Mohr. Yeah? So that point is going to be located in this quadrant here, fourth quadrant. Then, according to, let's put it here. Which color here? Let's call it Rankines. And here, Rankine, like this. Then in Rankine's terms, what's going to happen is that, simply stated, you have to take the maximum principal stress, as we said in class. You have to take the maximum principal stress and compare it with the either ultimate strength, or this one here, ultimate strength in tension or ultimate strength in compression. Yeah. So this value, the maximum stress, is sigma 1, and that has to be compared with something. In this case, as this is positive, this value is positive here, has to be compared with the tension value of the ultimate, well, the tension value, yeah, for the ultimate strength of the material. Yeah. So this has to be compared against this sigma ut, ultimate strength in tension, because we're talking about a positive normal stress, and positive normal stress indicates tension. Yeah. So this translates into what? Well, that 220 times, or point this one, has to be compared with 280, which is given here, in here in tension, or in here in tension. Yeah? Well, what does it mean? That for this case, now according to Rankine's, this is not going to fail because the ultimate strain in tension is larger than the stress applied. Then this is nothing is going to happen here, so it doesn't fail. And that is right. According to Rankine, does not fail like this. But perfect. And then if you could notice that it's going to be somewhere around this area here. No, it's not going to fail. Now, what happens with von Mises? Von Mises here. I'm going to write von Mises. I should write it in uppercase. I've seen it written in both cases, upper and lower. It would be nice to put this underline here. This one here. Perfect. Von Mises says, now von Mises' limit in the fourth quadrant is represented by this line here. In the other quadrants, for example, in the third quadrant or first quadrant, they are equivalent to Rankine's appreciation. But in this case, in the fourth quadrant and second quadrant, they are represented by an inclined line. The equation for that inclined line is represented as this. Sigma 1, let me write it better, sigma 1 divided by sigma ultimate strength in tension plus, no, actually this has to be, because this is the equation of a line, straight line, so this has to be minus this one here, divided by the ultimate strength in compression, and that has to be compared, no, that has to be compared with 1 actually. Let me write a more beautiful one here. I think so, more beautiful one. All right. What is left is substitute things here, so let's do it. We just need to calculate this, so let's put it. It's going to be 228.679 divided by this 280, and then this minus sigma 3 minus 148.679 divided by this, what is it, 410. And again, comparing, so we can close this in brackets to make it more readable. And let's go to the calculator. We have 228.679. I had it before, but let's write it down again. Minus 10 what? Minus 148.679 divided by 480. And this is equal to, look at this, 1.2, it's 228, 280, yeah. Sorry about this, this is kind of jumping at me, yeah. So this is 1.179, then compared to 1, this is larger, which means that, look at this, that according to von Mises, my goodness, Mohr, sorry about this, Mohr's theory, apologies for this, it's going to be, according to Mohr's theory, this is going to fail. It fails. Perfect. Let's do the same for the other cases then. Pretty clear, pretty straightforward. So then for case 2, here, this point formed by sigma 1 and sigma 3 is located, both are negative, and they are located in the third quadrant, which means that Rankine and Mohr, they are equivalent. Our big apologies, I ask you, for saying that this was von Mises. I don't know what I was thinking, but okay. So we have Mohr here. And I hope that I said more often. Okay. So they're located here. So whatever happens with one theory applies to the other, meaning that if it fails with Rankine, it would fail with Mohr's. Yeah, because they are the same at that point. And that's kind of important, say, characteristics with this. All right. So what we need to check here, according to these cases, is that what is the largest stress? Well, the largest stress is going to be this compressive stress here, this sigma 3. And what you have to do basically is compare it with the ultimate strength in compression here. And then you can write it in formula-wise. Actually, these don't fall, no, both Rankine, actually. Let me write Rankine and Mohr here, yeah. So what's going to happen, we're going to do more or less the same, is that you have to compare the maximum stress in this case with this one here, yeah. You can see it presented in a different way that you can say, okay, tell me how much is the relation, for example, between these two with respect to 1, yeah. What is the relation? Is larger, bigger, and so on. But basically what you're doing is that, saying is that if this principal stress is smaller than this one, then it doesn't fail. And also that applies to Mohr. Well, let's do that. So just let's do a plain comparison. So sigma 3 is minus 224.03, and then comparison strength is going to be 110. What happens here? This is smaller, so luckily or well designed, it does not fail. It does not fail. Not even in Rankine or in Mohr, because we said that in the third quadrant and in the first quadrant they are the same. Yeah, and this is an important distinction we need to consider. What's going to happen with the third case here? Well, at this point here, both are positive, which means that they are located in the first quadrant. And again, Rankine and Mohr are practically the same in that quadrant, so I can write here Rankine and Mohr. Again, underlining. And we're talking about positive values here. And if we're talking about positive value, then we need to compare the highest positive value with who? With the ultimate strength in tension. So basically, we need to compare. Here's another color. Sigma 1 with this one here. Let's write it down. So this would be nice to put here. Compare. This interrogation sign is compare. And here also. Then we're going to have that 300 megapascals. How much is compared to 80 megapascals? Is larger, which means that that state of stress case or a point or something that you were analyzing in the member or machine element you are designing is going to fail, according to both theories. And this is the analysis of this problem. Let's summarize it. So we have given a cast iron element. Now, this is very important to mention at the beginning that when we talk about cast iron, we usually talk about brittle material. Yeah, so that's why they're asking us to compare it with the two failure theories for brittle materials given in class. Right? Then we have 3 state of stress cases, which corresponds maybe to the same point but with different orientations, or it could be 3 different points on an element member. And what we do is, for each of these cases, calculate or extract the stress tensor, as we have it here. Simply extraction, respecting the sign convention given by von Karman. We also have here depicted schematics of what is the Mohr's theory of failure, this one here, and then what is the schematic of the Rankine's or maximum principal stress theory, or maximum principal stress theory. So what we do after this, we calculate the principal stresses using the formula for plane stresses, plane case stresses. That is very simple like this. And we are getting these 3 points here. So look at this, that these axes are sigma 1 and sigma 3, so that would allow us to determine in which quadrant are these points located, because they're going to tell us which part of the failure theories to use. For the first case that we're talking of a point, or about a point that is in the 4th quadrant, I should have written this because it's messy. This was in the 3rd quadrant, and this one's in the first ST here. ST. Oh, this is the first quadrant. Yeah. We have that for this case. Well, in Rankine's theory, it's not going to be the same as Mohr's theory because we see this big difference. This is the area for Mohr, and this is the area for Rankine. So what we do in Rankine is take the maximum principal stress and compare it to the corresponding one. If it's in positive with the tension one, and if it's negative with the compression one. We're talking about the ultimate strength of the material. And it tells you, according to Rankine, that does not fail. But when I analyze it, and I try to check if that point is contained in this area here or below, when I say below here, this line here, I use this formula, that is this formula here is the formula of this line here. And when I validate or check everything with the calculator, it says that according to Mohr, fails. I do the same for the second and third cases. Luckily, they fall under the third quadrant and then the first quadrant, meaning that Rankine and Mohr behave the same or practically the same. And what we need to do is simply a plain comparison between the maximum strain and the maximum ultimate strength. If positive the principal stress, then the tension ultimate strength. And then correspondingly, if negative the principal stress, then to the corresponding compressive ultimate strength. That's why here we compared this one, which is the maximum is in compression. I compared it to the ultimate strength in compression. But in this case, the maximum principal stress was in tension, so I compared it with the ultimate strength in tension. For second case, it doesn't fail. For the third case, it fails. What else? Well, this was it. We use a couple of tricks in the calculator to speed up the calculation process, but this is the end of the problem. If you have any questions, please let me know in the comments and we will try to get at it as soon as possible.